Hi there. Let's go through your homework questions for today. 11.55 was an odd question, so I hope you looked this one up. With only 20% power, this study shouldn't be run. That power represents the likelihood that we reject the null hypothesis when we should. Well, if we're trying to detect an important effect, the likelihood that we actually reject and are able to detect this effect is only 20%. If it's really that important, we shouldn't run the test. We should redesign the test first. Question 11.72 involves dealing with a confidence interval, and in particular, dealing with conducting a statistical test by using a confidence interval. This is the 90% confidence interval for the hourly earnings for American workers in 2000. So part A of the question asks, if we created a 95% confidence interval, would it be wider or would it be more narrow? And it would be wider, and here's why. Again, if you think about the way a confidence interval is constructed, we're going to take the sample mean, and then we're going to add and subtract the margin of error, but the margin of error is found by using the critical value, that would be in this case a t-score, and then we would multiply by the standard deviation of our sample, and we would divide by the square root of the sample size. What changes for 95% confidence would be this critical value, this t-score right here. For 95% confidence, it would make this critical value larger. That would make the margin of error larger. So you would be adding and subtracting a larger amount to the mean. That would make a wider interval. So part B, if you wanted to conduct the test of the null hypothesis of 16 versus the two-sided or the two-tailed alternative not equal to 16, in this case, the null hypothesis would not be rejected using an alpha level or a significance level of 0.1. So that 0.1 comes from the fact that we're using a 90% confidence interval, so that leaves us a 10% level of significance. Notice that 16 is in the 90% confidence interval. It is one of the possible candidates for the true hourly earnings in 2000. So I shouldn't be able to reject it. What's really going on here, because that value is in the confidence interval, the p-value is going to be larger than this 0.1, so we're not going to end up rejecting the null hypothesis. The opposite happens in this second case here. So notice that 15 is not within the confidence interval, it is outside of the confidence interval. So that means it is not a candidate for what could be the true hourly earnings for American workers in 2000. That means we should be rejecting this null hypothesis value. We will be rejecting it because it's not in the confidence interval. That means that whatever p-value we get, it should be less than 0.1. I can't calculate necessarily what it is, but I know it's going to be less than 0.1 so that it gets rejected. Again, we need to reject it because it's not within the 90% confidence interval. Question 1218, the population parameter, this involves an average difference or a mean difference between the yields of the two types of tomatoes, A and B. So in part B, when I wrote the null and the alternative hypothesis, I put a little subscript next to mu representing the mean difference. So I'm taking the yield of A and subtracting the yield of B from each plot. So I'm looking for the likelihood that A has a higher yield, so I'm looking for positive differences. That's my alternative hypothesis. It's a greater than zero hypothesis. We don't have the data, so we're not able to verify the conditions, but we should still write about them. We should act as if these 10 differences are a random sample of yield differences between the tomato varieties. We have to believe that 100 is less than or equal to the number of possible differences that we could produce if we took plots of land and plotted both varieties of tomatoes on them. Notice with n equals 10, the central limit theorem doesn't apply. This is a question about mean differences. Because it's a question about means, it involves the central limit theorem when it comes to normality. The central limit theorem doesn't apply. So we would want to inspect the sample data. Since we can't, we have to act as if there's little skewness and no outliers within those sample differences for us to believe that the sample mean differences are approximately normally distributed. So the one sample t-test, if you run it on your calculator, this is the t-score that you should get, 1.295. This is the p-value that you should get, 0.1139, with 9 degrees of freedom. Let me take a second and put that into the calculator just to make sure that you're okay with that. Over to tests. This is a t-test, so I want to enter the statistics. So the null hypothesis value is 0. The sample mean, I don't remember the actual sample mean. Let me go and grab it really quick. Sorry about that. I had to go grab my book regarding the original data. Let me turn to it real quick. Okay, here we go. So the sample value that we were given was a mean difference of 0.34. The standard deviation was 0.83. There is the sample size. The alternative hypothesis is greater than. So there's how I got my t-score. There's how I got my p-value. Again, this is a one sample t-test. So we're ready to interpret our result. So with this p-value, which is greater than 5%, we cannot reject the null hypothesis. So writing about the alternative in context, I don't have any evidence suggesting that the actual mean differences in yield between these two tomato varieties is actually greater than 0. So that's what a complete significance test would look like in this context. So going on to question then 1219. Regarding the error types and regarding the power, a type 1 error would occur if we reject but we shouldn't reject. So this would occur if we've rejected and the researchers believe that they have evidence that the mean difference in yield really is greater than 0, but they shouldn't have rejected the null hypothesis. So in fact, the mean difference really isn't any different from 0. A type 2 error, that would imply we have not rejected but we should reject. This would occur if the researchers believe that they really don't have evidence that the mean difference in yield is greater than 0, but they should have rejected that null hypothesis because in fact, there really is a mean difference that is greater than 0. Your job then was to decide which of these is more serious. Frankly, you could argue that either one of them is more serious as long as you interpret the type and the consequences appropriately. I personally think a type 2 error is more serious. I mean, a type 1 error, whether you plant one variety of tomato or the other variety of tomato, probably doesn't cost that much to plant one variety over the other variety. And if there isn't much of a mean difference, you're really not losing much either way. However, with a type 2 error, if there really is a difference between the yields of the two varieties, I would prefer to plant the variety that has a higher yield. As a farmer, I'd make more money that way. So regarding the power of the test then, one of the most important results from yesterday is to recall that if you leave everything else equal, increasing the sample size should increase the power. So the power with a sample size of 10 is about 0.53. If we increase the sample size to 25 in part C, the power rises to approximately 90. So again, to calculate that, you want to use the power test program. I'm going to go ahead and run that here. So if you go to the program button, again, if I put the power test program on your calculator, execute that test. This is a test involving a mean. This is a null hypothesis value of 0 because I'm looking for evidences of differences that are greater than 0. This is a one-tailed test. It's a greater than test, so it's a one-sided test. The standard deviation that I have to work with is 0.83. The sample size that I'm working with in part B is 10. The level of alpha is 0.05. That's what was specified. The true value that we want to make sure we have enough power to detect, the true difference that's larger than 0 that we would really care about is half of a pound per plant. So that's the value of the alternative that I want to make sure that I am able to detect. I will put that in as the true value or the value of the alternative hypothesis that I want to make sure I can detect. So pressing enter, there's the power of the test, 0.53. Remember that this is 1 minus the power of the test. This is the likelihood of a type 2 error, 0.47. Remember the likelihood of a type 1 error, that is your level of alpha, 0.05. So for part C, all I'm going to do is change the sample size to 25. So you have to press enter to get the program to stop running. I'll run the program one more time. We'll put in the same values, so it's a mean question again. The null hypothesis value is 0. We're working with differences. It's a one-tailed test with a standard deviation of 0.83. I've increased my sample size to 25, so my power should rise as long as I'm leaving alpha the same. So I'm leaving the likelihood of a type 1 error as 0.05. Again, I want to be able to detect a true mean difference of 0.5. And there you go. The power of the test is approximately 90. So I have increased the power to 0.90, which that also decreases the likelihood of a type 2 error all the way down to about 10%. So again, I don't expect you to use the power test program on your test. I don't expect you to be able to do power calculations on your test. I would want you to know that alpha, or the level of significance, that's the likelihood of a type 1 error. And if you know the power, I would want you to know the relationship that the type 2 error can be found by taking 1 minus the power. I would want you to know that relationship. And of course, it's important to recognize the big lesson here that if you want additional power, keeping all other things equal, one of the smartest things you can do is increase your sample size. Hope this has been helpful.